back to our study of differential calculus, and today we begin chapter 4, where we talk about applications of the derivatives. Now we've studied we've studied what a derivative is, what its definition, how it was defined in terms of limits. We've seen how the derivative gives us the instantaneous rate of change of a function. Now we're going to use that instantaneous rate of change in order to solve some problems. We have used it in the last chapter. We've done, I would argue, we've already done some applications, related rate problems or linear approximations. But in chapter 4, we'll add to that problem-solving ability. Now, in this section, 4.1, we're talking about extreme values. That's an E, extreme, or maybe I'd refer to as mins and maxes. Okay, extreme values, mins, minimums, and maximums. Okay. Now, first of all, we start with, we look at this function. Let's look how easy the concept is. First of all, I'm looking over here, and I've got this function f of x, and I've got it defined over a domain A to B. And you'll see if you follow this function, you'll see at point A here, we've got a min, right? We'll call this a local min. In that area, in the area around A is the lowest point. Okay, local minimum. Here's another local minimum here. Why don't we, well, let's call this x1. Let's call this x2. Let's call this x3. And you'll see at x2 we have another local minimum right here. We have another local minimum at x2. So our local minimums might be x1. Oops, x1. Nope. Try that again. It's A at x equal to A, at x equal to x2. Right, in that neighborhood of x2, x2 is the minimum, and we got another minimum over here at B. All local, what we refer to as local minimums. Well, what do you think a local maximum? A local maximum, of course, is the largest value of the function, and you'll see you get local maximums at what x values? x1, comma, and then right here at x3. At x3. Okay, so those are local. They might use the term absolute. Like we might ask the question, what's the absolute lowest this function can take on over this term? And then the absolute minimum is basically you look at all the minimums, all the local minimums, and pick the lowest. So it's not A. Well, it looks like x2 is a little lower than A, but look at B. B is clearly in this case at x equal to B, that is the x value where the function takes on its absolute minimum. If you wanted to turn that into a point, for instance, you'd say, well, at x value B, well, what's the function at that? It's f of B. So f of B is the lowest y value in that region. Well, what about absolute maximum then? Absolute maximum, well, which one is that? Is this max? This max is certainly bigger than that max, right? It looks at x3. x3 is our absolute maximum, so I'd say at x3, the function fx takes on its largest value. And if I've turned that into a point, I'd say at x3, well, what's the function equal to there? I'll just write it down as such. Okay, why are we interested? Again, calculus is all about functions. It's all about these functions. Maybe this turns out to be the unemployment rate, and we'd like to minimize this. We'd like to find out how to drive it to its minimum point. Or maybe it's a stock market graph, and we'd like to know, when is this thing going to hit bottom so things start improving? Maybe it's housing housing data from the economy. So these aren't just boring old functions. These functions mean something to us that are important, and finding the maximum spot might be advantageous for our problem, or maybe the minimum, maybe minimum unemployment, maybe maximum return. Continuing on then with our application of the derivative, again, we are interested in finding maximum and minimum values. And here's a theorem that you don't need to remember the guy's name, although it's always nice, impressive on any Jeopardy challenge. But in your book, it's listed as Fermat's theorem. And what it says here, it's a theorem of finding local extreme values. What's an extreme? Extreme is a minimum in the function or a maximum in the function. And it says here, if f of x has a local max or min at an interior point, okay, interior point, I circle that here, C, okay, C is an interior point, and if f prime of z exists, what do you think it's equal to? So here's my little picture over here. My little picture of a graph. I've got f of x, I've got x, I'm going between a and b, and it turns out I say the interior point C, see right here, the interior point, if the interior point is a max or a min, and the derivative exists, well, what's it going to be equal to? F prime of C is going to be equal to what? Well, guess what? Horizontal tangent, right? It's got a horizontal tangent line, so the derivative is going to be equal to 0. Going to be equal to 0. So you'll start using that a lot. If you want to minimize or maximize a function, you set the derivative equal to 0. Okay, and this is where it starts from. But remember, in this theorem, a couple of things here. I want to look at, in order to understand it, I want to look examples where the theorem doesn't hold. Okay, the theorem doesn't hold. And a lot of times, one of my favorite counterexamples for all the continuity or the limits existing or derivatives existing is what? It's an absolute value function, right? So here's my absolute value function. And you'll see this is an absolute value such that, right, this is a peaky point here. This is C. Notice this is the max, f of C. It's a max. Okay, so f of x has a local max or min, so it is. It's a max, okay, it follows that. It's interior point, and it says if f prime exists, okay. Does f prime exist here? No, it doesn't. Okay, so f prime of C is the old do not exist. So here's a case where the derivative is not equal to 0 in this case, okay? The derivative is not equal to 0, and I'll just maybe draw something like that and put an x through it. It doesn't follow the theorem. Okay, let's try another one. Well, how about something like this? Here's a function, and it's just y equal to x. Here's a. Here's b. This is a function of x equal to x. Well, here's my max. Here's my max. Here's my min. Okay, so I have a max or min. Does the derivative clearly f prime of b is not equal to 0. F prime, the derivative of a, is not equal to 0. Why does this fail? Well, it's not an interior point. Okay, a and b are not interior points in this case. But as the theorem says, if you get an interior point, that's a max or a min, going back to here. If interior points are max and min, if the derivative exists at C, the derivative must be equal to 0. A lot of times you will be given problems where you're interested in finding the absolute max or min of a function on a given interval. Again, these functions are like, this is what we're interested in. They model real life behavior, and we're interested in the best possible answer. And here we'll use the theorem we just looked at and its caveats to find that. Now, so it says extreme values here. Just read this through with me. Extreme values, what are those? Those are maximum or minimum values on a function of a continuous function. We know what a continuous function is, right? You can't lift your pen off the paper. On a closed interval a, b, right? A closed interval includes the endpoints, a and b. We say we can exist, extreme values can exist at x equal to c when what is true? Well, if it's an interior point, if the derivative exists, well, the derivative is equal to 0. If it's an interior point and the derivative does not exist, remember, like the absolute value, that also might be a case. Or, well, maybe it's not an interior point, or C is an endpoint. And I would just remind you, check all three cases to find extrema. You'll heard it called extrema, another term for max and mins. Okay, another definition. You'll see this ad, you'll be asked, find the critical points of a function. Find the critical points. And what would that mean? Well, when we say critical points, we'd say a point in the domain of f of x where either the derivative is equal to 0 or the derivative does not exist. Okay, so remember, just to give you a little graphical of this. Whoop. Well, here's critical points. Well, I could have, the derivatives are equal to 0 here, and here, and here. Those are critical points. Where doesn't it exist? Well, how about an absolute value function? Okay, right here, this derivative doesn't exist here or here. Okay, these could be a do not exist point. Both of these points and this point here, I guess in this case, these are critical points. Critical point here, 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 right here. This would be f prime equal to 0, and here's where it doesn't exist. F prime, that's a do not exist. All our critical points, you need to check them all to find max and mins.